Okay, so in this video we're going to continue talking about standing waves and doing calculation problems with standing waves. Now remember, standing waves are formed in situations where you have boundaries where reflection can happen, and the idea is that, the waves reflect at the boundaries and they can cause interference with each other when they pass through each other, and under the certain conditions you can get these so-called standing waves where energy appears to not be transferred in the waves. Okay, so we're going to start off by talking about standing waves on a string, and the boundary condition that we're going to focus on for a standing wave on a string is that the two endpoints must be nodes. And in the last video we talked about how a node is a point on the wave which appears to not be moving. Okay, so let's take a look at what this looks like. Okay, so let's say we have a string, and the length of the string is L, and let's say we create the most basic standing wave we can imagine. Okay, and that standing wave would look like this. Okay, so we have a node at the two endpoints, and in the middle we have an antinode, which is the point where we have maximum displacement along the standing wave. In terms of interference, that's the part of the standing wave where we get constructive interference between the two waves that keep reflecting back and forth at the end. And what we have here is what's called the first harmonic. Now, if you look at the length and you kind of use your imagination, and it tries to show you this on the picture here, you can see that the length of the string is actually half of a wavelength. Here you can see basically the up part of the wave, and then over here they've kind of drawn the down part of a wave off to the side, and so this length of the string in the first harmonic is half of a wavelength. Okay, and so this is what we call the first harmonic, or sometimes called the fundamental frequency. The frequency at which the standing wave is formed is the lowest possible frequency for which you can get a standing wave to appear on this string and still satisfy the boundary conditions. Okay, and so at this first harmonic, at this frequency which we call F1, we get the most basic type of standing wave you can imagine. Okay, and in this situation you can see visually that the length of the string is half of a wavelength. Now, notice an equation popped up here, F1 equals V divided by 2L. Okay, so where does this F1 equals V over 2L come from? Well, basically, based on the boundary conditions and based on this picture, you can see that the length of the string, which is L, is half of a wavelength, which means that the wavelength has to be equal to 2 times L. It's just rearranging that equation. But because of the wave equation, which is V equals lambda times F, we can actually plug in to this, and we get V over lambda, which is V divided by 2L. Okay, and this is what we call F1, the first harmonic, or the fundamental frequency. Okay, and so if you vibrate the string at this frequency, you will produce this type of standing wave. You'll produce the first harmonic. Okay, so that is an equation that is not given to you. That is something that you would derive, just like we just did, based on the picture that you drew, recognizing that the length is half of a wavelength, and then using the wave equation to rearrange and solve for frequency. Okay, now this is not the only type of standing wave you can get, but this is the most basic one. Okay, so this is the first harmonic. Notice, by the way, that if you look at this equation, we have F1 equals V divided by 2L. V, remember, is the wave speed. Okay, now, different factors affect wave speed. You do need to know that the factors that affect wave speed for a string, there's two of them. One is the tension in the string, and the other is what's called the mass density of the string. Okay, and so an analogy from for a musical instrument might make more sense. If you've ever played a guitar, then you know that number one, you can tune a guitar by tightening the strings at the end. Okay, so by adjusting the tension in the strings, you can affect the frequency of the standing waves produced. Okay, the other thing, mass density, basically if you've ever looked at guitar strings, you hopefully notice that they're not all the same size. Okay, some are thicker than others, and so that's kind of what we mean by mass density. Basically, how much mass they have per unit length. Okay, so those are the two factors that affect the wave speed for a string. Okay, so if you've ever played a string instruments, there's a few different ways to affect the frequency that is played. Okay, the first is obviously you can adjust the tension or the mass density. It's not really practical to do that while you're in the middle of playing a musical instrument, but you could do it, in between performances or whatever. More practically speaking, the other factor that affects frequency of a standing wave is length, the length of the string. And so if you've ever played a string instrument, usually what you are doing to change the frequencies, you're changing the length of the string by holding down different parts of the string and basically making it longer or shorter by placing your fingers at different points along the string. Okay, so that's just kind of an aside, but I wanted to talk about that. So this equation we've derived here is only for the first harmonic. In a second, we'll look at equations for other harmonics, but make sure you add this to your notes. Okay, so moving on. That's just talking about the derivation we just saw. Okay, so what happens if you increase the frequency? You'll get higher harmonics. This is basically what I just talked about before. I can link some videos in so you can see what this looks like. But in the top picture here, you can see if you just play a guitar string without, holding down the string at any of the frets, you basically get a longer standing wave. Whereas if you're actually playing the instrument, when you hold down the string, let's say down here, you basically effectively decrease the length of the string, which tends to increase the frequency that you play on the musical instrument. Okay. So that seems to be easier to do than spontaneously tightening the string to change the tension in the middle of a performance. Okay, so I'm going to link some videos in so you can see some more applications, standing waves, and then we will see some higher harmonics on the next slide. Okay, so like we said before, the first harmonic is not the only possible standing wave you can get. Okay, you can get different types of standing waves as long as they meet our boundary conditions. And remember, our boundary condition is that the ends have to be nodes. Okay, so here's another type of standing wave that meets those boundary conditions. Okay, it looks something like this, where it goes back and forth, back and forth. Something like this. And notice now we actually have 3 nodes and 2 antinodes. Remember, antinodes and nodes always have to alternate. Okay, and so this is what we call the second harmonic. Okay, so why do we call this the second harmonic? So remember, the length of the string is L. And the way you approach standing wave problems is you always ask yourself, okay, so in terms of L, how many wavelengths am I looking at? Okay, and hopefully you can tell by looking that the length of the string is equal to 1 wavelength. So L is equal to lambda. We have the up part here. We have the down part here. This other bit that's drawn in is just the reflected part of that. So the down part and then the up part. Okay, it just goes back and forth like that. So here in this case, L is equal to 1 full wavelength. And again, going back to the wave equation, we have V equals lambda times F. Here we get F equals V over lambda, which is equal to V over L. And this we call F2, which would be the second harmonic. Okay, now I want to point something out. The first harmonic for a wave on a string was V over 2L. V over L is 2 times V over 2L. Because if we were to multiply this by 2, we'd get V over L. In other words, what I'm saying is F2 is equal to 2 times F1. Okay, so the second harmonic, by definition, is twice the frequency compared to the first harmonic. Okay, so this is the second lowest frequency you can possibly get and still meet the boundary conditions. And so this is what we call F2, the second harmonic. Okay, and you can get higher and higher and higher harmonics as you go down. It's the same, it's basically just like a multiple of the original frequency. Okay, and if that seems strange to you, just think in terms of musical instruments, it's kind of like how there's different octaves and things like that. You know, you can have the same fundamental frequency, but have higher harmonics on top of that. Okay, so it's the same type of thing. So imagine what the third harmonic would look like here. Okay, so you have F1 is V over 2L, F2 is V over L. Any guesses what F3 is going to look like? Okay, so hopefully you figured out the pattern. F3, by definition, if it's the third harmonic, it should be 3 times the first harmonic. And so it's actually going to look something like this. Notice the way we get this picture, and this is something you need to know because you need to be able to draw these harmonics, is to go from the first to the second harmonic, we basically added a node. Okay, we went from 2 nodes to 3 nodes. To get to the third harmonic, we're going to add another node, so we have 4 nodes overall. And it's going to kind of be broken up into fourths, as you can see, because it always has to alternate node, antinode, node, antinode. Okay, so here we have 4 nodes. We know we have to have antinodes in between those nodes. And so it's going to look something like this. And if you ask yourself how many wavelengths do we have in L, here we have 1 wavelength and then a half wavelength. So I would say L is equal to 3 halves wavelengths. Okay, we have 1 lambda plus a half lambda. That's 3 lambda over 2. And if you rearrange that equation, you get 2L over 3 equals lambda. And if you plug into the wave equation and solve for frequency, then you get 3V over 2L is equal to F3. And that is the third harmonic. Notice that it is exactly 3 times more than the first harmonic. Okay, so again, these equations here, make sure you finish adding that to your notes. Notice that none of these equations you would be given on a test. You would have to derive all these equations just like we've done here. Remember, just to go up to the next highest harmonic, you're basically just adding another node. Okay, as long as you understand what the picture should look like, then you can understand how the length relates to the wavelength. And if you can do that, then you should be able to use the wave equation and solve for frequency. Okay, so you should be able to derive all of these equations and even higher harmonics if you needed to, based on the boundary conditions. Okay, which in this case, the boundary conditions are the two endpoints are nodes, and then you just keep adding a node from there. And this is kind of what the higher harmonics would look like for a wave on a string. Practically speaking, you usually don't see any higher than the fifth harmonic on IB equations, just because it gets kind of crazy to draw and to do those calculations. But it is pretty common to see the second or the third at least. Okay, so again, note that the second harmonic is twice the first harmonic by definition. The third harmonic is 3 times the first harmonic, etc., etc. Okay, if you wanted to, I guess you could just memorize all these equations, but I find it easier to just understand the concepts and then rederive the equations just like I just did. Okay, so quick example. In the image to the right, which harmonic is this? Okay, well, this is, if you go back to our reference chart, this has 4 bulbs, so this is going to be the fourth harmonic. And that's pretty easy to tell. The second question says label the antinodes with an A and the nodes with an N. Okay, remember the nodes are the points on the standing wave that appear to not be moving. So these are going to be the nodes. and then the antinodes are going to be here. Okay, so those are the antinodes. Determine the wavelength of the standing wave shown. So if this whole thing is 4 meters, you should be able to tell how many wavelengths we have here. We have one back and forth, and then we have another back and forth. So L is equal to 2 lambda. But if you look at the picture, we know that L, the length of the string, is actually 4 meters. Okay, so we should be able to figure out that the wavelength here is actually 2 meters. Because 4 divided by 2 is 2. So there you go. There's the wavelength of the standing wave. Let's see. The fourth question says, calculate the frequency of this harmonic assuming a wave speed of 120 meters per second. Okay, so remember that V equals lambda times F. Okay, so we're looking for F, assuming that we know V and lambda, which we do. V is given as 120 meters per second, and the wavelength is 2, so that would be 60 hertz. Okay, now the last question says calculate the fundamental frequency, that means the first harmonic of this wave, assuming the same wave speed as the previous question. So see if you can figure that out on your own. Okay, so hopefully you realize that this is F4, this is the frequency of the fourth harmonic, which by definition, F4 is 4 times F1. So if we know F4 is 60, that means F1 should be 15 hertz, because that's just a fourth of 60. Notice, by the way, that the question says assuming that the same wave speed as the previous question, which makes sense because, as far as we know, the tension of the string hasn't changed, and also the mass density hasn't changed if it's the same string. Okay, so pause there if you need to finish looking at that. Okay, so moving on. Okay, so now we're going to finish up by talking about standing waves and pipes. Okay, so we talked about standing waves and how they can be created on a string when the two ends are fixed. So we're going to look at 2 types of standing waves that can be formed in pipes. Okay, so here are the 2 types. Number 1, pipes open at pipes open at one end but not the other end. Like, for example, clarinet or an organ. One of the ends is closed off. Okay. The other type of pipe is pipes that are open at both ends, like a flute, or a trumpet, or a recorder. Okay, again, knowing and understanding the boundary conditions can stop you from having to memorize a bunch of equations, which I guess you could just memorize them if you wanted to, but understanding concepts is maybe easier to do. So let's see what these pipes look like. Just to kind of recap really quickly, remember that V, the wave speed of the pipe, refers to how fast the wave travels through that medium. And so for a string, that depends on the tension in the string and the mass density of the string. Generally speaking, for sound moving in a pipe, V is the speed at which sound travels in air. Although technically speaking, you could put, some other type of gas in there besides normal air, and that would affect the speed of the sound wave. Okay, that's one reason why you sound different. If you breathe in certain types of gases, you can make your voice change and get higher or lower, because that changes the speed of air in your lungs. Okay, so typically for a pipe, those would usually be fixed values for any given situation. Okay, so let's start with pipes open at one end. It's important that you understand the boundary conditions for a pipe open at one end because the standing waves here look a little bit different. So here are the 2 boundary conditions. Number 1, the open end of the pipe has to be an antinode. And the reason for that is if the pipe is open at one end, the air can move freely at that end, and so it can reach a maximum amplitude at the end point. The closed end of the pipe has to have a node because the air molecules can't move there because it's closed. And so that has to be a node of the standing wave. Okay, so based off of the boundary conditions I've described, here is what the first harmonic for such a standing wave looks like. So here's a pipe that's closed at one end. We have to have a node here. We have to have an antinode at the endpoints. Now remember, nodes and antinodes have to alternate. So we don't actually need anything other than one node and one antinode. The first harmonic for this type of standing wave actually looks something like this. Okay, and that's it. Here, we usually say the length of the pipe is L. So I will come back to this on the next slide where I have more space. Okay, but make sure you add this picture to your notes so far. Okay. So here's the first harmonic, and we can see that the length of the pipe is L. Okay, how much of a wavelength do you think this is? Well, it actually turns out that this L is actually a quarter of a wavelength. You can imagine a full wavelength has an up part and a down part. Half a wavelength would have either a whole up part or a whole down part. This is like half of an up part right here, from here to here. So this is actually a quarter of a wavelength. That means when you calculate the first harmonic frequency, you get lambda equals 4 times L. And so F equals V over L, or V over wavelength, just rearranging the wave equation. And that is equal to V divided by 4L. And this is F1. This is the first harmonic for a pipe open at one end and closed at the other. Okay, F1 equals V over 4L. And again, that's not an equation you're given. You would be expected to derive that on a test or on a quiz. Notice that it's basically the same factors that affect the frequency, though. Okay, so you can't practically change the speed of air inside your pipe very well, but you can change the length of the pipe. And so usually what you do, if you're playing a musical instrument with a pipe, is you change the effective length of the air column by moving your fingers around and closing different holes along the musical instrument, and that effectively changes the length of the air inside your pipe, which changes the frequency. And so that's how you play different notes. Okay, so we have F1 equals V divided by 4L. Keep that in mind, and let's think about what the next harmonic might look like, because I'm going to erase this. Okay, so remember, to go to the next harmonic, we have to add another node. But if we add another node, we also have to add another antinode, because those two have to alternate. Okay, so we're actually going to get something that looks like this. Notice here that we have a full up part, and then we have another quarter. So basically we have half of a wavelength plus a quarter wavelength along the length. Okay, so L is now equal to 3 lambda over 4. Okay, it's 3/4 of a wavelength. Now if you rearrange this, solve for lambda, you get 4L over 3. You plug into the wave equation like we've been doing. You actually get V, you get a 3 on top, you get a 4L on the bottom, and then you notice something funny. Remember that F1 was actually equal to V over 4L. If you compare this equation to this equation, notice that this equation is 3 times this. That means this is actually the third harmonic, not the first, or not the second, it's actually the third. So you might ask yourself, wait, what happened to the second harmonic? Where did it go? Well, it doesn't exist. Okay, for pipes open at one end and closed at the other, you do not get even harmonics. You only get odd-numbered harmonics. Okay, so for this type of pipe, we have the first harmonic, the third, the fifth, the seventh, and so on. It just, because of the boundary conditions, we only get the odd-numbered harmonics, which I always thought was kind of a strange thing, but that's how it goes. It's just because of the boundary conditions. And again, this is the third harmonic because it is 3 times the first harmonic, which by definition makes it the third. A couple of years ago, there was a question on the IB exam where they gave this type of pipe and they asked the students to calculate the second harmonic, and all the IB teachers got upset because there is no second harmonic for this type of pipe. Really what they meant was the next highest harmonic, which would be the third. So they had to throw that whole question out that year. But anyway, make sure you add that to your notes. I'm going to go to the next slide. Okay, and most of this is not new information. This is basically just showing you what the first 3 harmonics look like for a pipe open at one end and closed at the other. Okay, you have quarter wavelength, 3/4 of a wavelength, 5/4 of a wavelength, and so on and so forth. Okay, keeping in mind the boundary conditions, you have to have the open end has to be an antinode, and the closed end has to be a node. Actually, it looks like it's kind of drawn backwards here. I apologize for that. They have it drawn so the antinode is on the closed end. It's actually flipped from how it should be. So, sorry about the picture being a little bit backwards. Okay, so I am actually going to stop the video here, and I think I will do one more video next class just to finish up talking about standing waves so that we can get ready for our test. As always, please let me know if you have any questions, and I'll see you guys in the next video.